The last of the fundamental bonding concepts that we will look at for now is electronegativity and the impact it has on electron distribution and bond polarity within molecules. Electronegativity refers to the ability of an atom in a bond to draw valence electrons to itself. The electronegativity of the atoms and elements is usually measured on the Pauling scale, which is a unitless scale where fluorine at the top right is the most electronegative element and has been arbitrarily assigned the maximum value of 4. The electronegativity values of all the other elements are then measured relative to the electronegativity of fluorine, and those values are shown in this version of the periodic table. The differences in electronegativity of elements arises from differences in nuclear charge, differences in atomic size, and differences in the number of core electrons. As a result, some elements have a greater ability to attract bonding electrons to themselves, or in other words, have a greater electronegativity. The electronegativity is a periodic property of elements, and its magnitude generally increases across a period from left to right and increases as we go up a group or decreases as we go down a group. This means that nonmetals at the top right of the periodic table, with the exception of the noble gases, have the highest electronegativities, and metals in the bottom left have the lowest values. Elements with high electronegativity have a greater ability to attract valence or bonding electrons to themselves compared to other atoms. The implications of this is that electron distribution within bonds, when electrons are shared between atoms, is typically uneven. And this is important because the size, the shape, and the electron distribution within atoms, molecules, and ions tends to dictate the physical and chemical properties of most substances. For example, let's consider 3 different types of substances. Cl2, which is a molecular element, the molecular compound hydrogen chloride, HCl, and the ionic compound sodium chloride, NaCl. Elemental chlorine is formed from 2 single chlorine atoms, each with 7 valence electrons. When the 2 atoms are brought into close proximity, these 2 electrons are shared across both atoms to form a covalent bond, with the end result that both atoms gain an octet of electrons in their valence shells. In this case, both atoms are identical and both nuclei attract the bonding electrons equally. The result is an equal or symmetrical distribution of electron density between the 2 atoms. We refer to this type of bond as a nonpolar covalent bond. The hydrogen chloride example is different. A single hydrogen atom has 1 electron in its valence shell, and the chlorine atom has 7 electrons in its valence shell. When the 2 atoms are brought into close proximity, these 2 electrons are shared across both atoms to form a covalent bond, with the end result that the hydrogen atom completes its duet of 2 electrons required for stability, and the chlorine atom completes its octet required for stability. The difference in this case is that the atoms are not identical. They have different electronegativities, with chlorine being significantly more electronegative than hydrogen. This means that the chlorine atom draws bonding electrons to itself to a greater degree than the hydrogen atom does, and we have attempted to represent this by placing the 2 dots representing the shared electrons closer to the chlorine atom. The end result is that we have an unequal distribution or unequal sharing of electrons between the 2 atoms in this bond, and the bond is said to be a polar covalent bond. We can consider the polar covalent bond as an intermediate bond type between the nonpolar covalent bond that we just saw in the Cl2 example and the ionic bond, which is the type of bonding we see in our next example, sodium chloride. The sodium chloride compound is made up of positively charged sodium ions and negatively charged chloride ions. The Lewis symbol shows that the sodium atom has lost its only valence electron, therefore leaving the cation with no valence electrons in its outermost n equals 3 shell. The chloride anion, on the other hand, has a complete octet in its outermost shell. The bond holding these 2 atoms together in this case is the result of the electrostatic attraction of oppositely charged ions, and we refer to this as an ionic bond, where the distribution of electrons between the 2 atoms is very much unequal. These 3 structures shown on this slide demonstrate the full continuum of bond types from nonpolar through polar covalent to ionic. We will discuss this continuum in a bit more detail in a moment, but I first want to illustrate another way of representing the unequal distribution of electrons within bonds. A polar covalent bond, or simply a polar bond, is a covalent bond in which there is an unequal sharing of bonding electrons, and on average the bonding electrons spend more time near the nucleus of one of the atoms compared to the other. The unequal sharing of bonding electrons in polar bonds is often represented by the use of the lowercase Greek letter delta, which is used to identify partial charges on atoms in bonds and therefore bond polarity. A delta minus symbol on an atom represents a partial negative charge and a relative excess of electron density around that atom. A delta plus symbol on an atom indicates a partial positive charge and a relative deficiency of electron density around that atom. Using this notation, the hydrogen chloride molecule would be represented like this, with the delta minus symbol placed near the chlorine atom and the delta plus symbol placed near the hydrogen atom. Now, the HCl molecule is neutral overall and has no net charge, but the chlorine atom has a relatively high electronegativity value, and there is a relatively high electron density around the chlorine atom, giving it a partial negative charge. The hydrogen atom has a relatively low electronegativity value, and there is a relative deficiency of electrons around it, giving it a partial positive charge. This uneven electron distribution is exacerbated by the fact that the two bonding electrons that are shared between these two atoms are drawn closer to the chlorine atom because of its high electronegativity, and these two bonding electrons spend, on average, more time closer to the chlorine atom than the hydrogen atom. The direction of the polarity in a polar bond can be represented using an arrow with a cross at its other end. The head of the arrow points in the direction of the partial negative charge, and the cross end of the arrow is placed near the atom with the partial positive charge. Bond polarity is characterized by differences in electronegativity values. Small differences in electronegativity values means the bond is relatively nonpolar. Larger differences mean the bond is relatively polar, and very large differences in electronegativity values mean that the bond is considered to be ionic. It should be noted that no definitive boundary exists between ionic and covalent bonding, and most bonds have both ionic character and covalent character. We can quantify the percent ionic character of a bond by using the difference in the electronegativity values of the atoms involved in a bond as shown in this table. And while there is no definitive boundary between ionic and covalent bonding, it is still useful to describe bonds using these labels. As a rough guide, we can say that bonds where the difference in electronegativity values of the two atoms is 2 or greater can be considered ionic bonds. Bonds where the difference is greater than 0.5 but less than 2 can be considered polar covalent bonds. And bonds where the difference in electronegativity values is 0.5 or less can be considered nonpolar covalent bonds. Although it should be noted that technically the only truly nonpolar bonds are bonds between identical atoms.